Hello my friends, and welcome back to the You Can Do TV channel. Alcoa's bauxite operations are defined by highly optimized, low-cost surface mining and precision ore management. Deposits are typically shallow, enabling open pit extraction without drilling and blasting, using excavators and haulage systems to maintain continuous material flow. Once extracted, bauxite is subjected to selective mining and grade control, ensuring consistent aluminum oxide content before transport to refineries. Advanced fleet monitoring and real-time tracking systems improve equipment utilization and reduce variability in production. Material handling integrates crushing, screening, and calcification to remove non-alumina-bearing fractions early, improving downstream efficiency. Alcoa maintains a stable, high-volume supply of bauxite, forming the technical foundation for efficient alumina refining and aluminum production. At Alcoa's Juruti bauxite operation, the lagoon system forms a critical backbone of sustainable mineral processing. After extraction, bauxite undergoes mechanical crushing and water-based washing, where vibrating screens and cyclones separate impurities without the use of chemicals. Water management is central to the operation. Over 70% of process water is recirculated through thickening lagoons, where suspended solids settle and clarified water is returned to the plant. Residual tailings are pumped into designated disposal lagoons, where they naturally dry and regain soil-like properties over time. Engineering design emphasizes safety and environmental control. Containment basins are built to handle extreme rainfall events, preventing uncontrolled discharge. When lagoons reach capacity, areas are rehabilitated using topsoil and native vegetation, restoring forest conditions. Continuous monitoring of groundwater and surface water ensures compliance, while emergency action plans and simulations provide operational resilience. In alloy wheel manufacturing, precision casting and lean production converge to transform molten metal into high-performance automotive components. At GMP Italia's foundry, advanced engineering systems guide every phase, ensuring structural integrity, dimensional accuracy, and repeatable quality. The process begins across 3 dedicated casting areas, where aluminum alloys are melted, refined, and poured into precision molds. Controlled cooling cycles minimize internal stress while preserving the intricate geometry of each rim. Automated handling systems then transfer semi-finished wheels through 10 production stations, where machining, inspection, and service preparation are executed with tight tolerances. Lean manufacturing principles streamline material flow and reduce waste, enabling a daily output of up to 1,200 wheels without compromising consistency. Each stage is optimized for efficiency, from casting to final finishing, integrating robotics and process monitoring for stable throughput. The result is a lightweight yet durable alloy wheel, engineered to withstand demanding road conditions while maintaining aesthetic precision and performance reliability. Inside AGM battery manufacturing, performance is not defined at the final test stage, but engineered from the very first transformation of raw lead into electrochemically active material. Each step is tightly controlled to ensure conductivity, structural integrity, and long-term cycling stability. The process begins with plate making, where pure lead is converted into fine powder through controlled oxidation. This lead oxide is then blended with water, sulfuric acid, and chemical additives in a calibrated mixing process, forming a uniform paste. The paste is applied onto stamped lead grids, creating both positive and negative plates with precise thickness and density. Following this, plates undergo steaming and drying, stabilizing the active material and improving adhesion to the grid structure. In parallel, grid manufacturing ensures mechanical strength and conductivity through precision stamping. During assembly, plates are wrapped with absorbent glass mat (AGM) separators, then stacked and inserted into battery cells. The structure is enclosed and prepared for electrochemical activation. The formation stage uses controlled rectifier systems to charge the cells, converting raw materials into active compounds. Afterward, acid filling saturates the AGM, enabling efficient ion transfer. Each unit undergoes high-rate discharge testing to verify performance under load, followed by cover sealing and packaging, ensuring durability, safety, and readiness for industrial deployment. In high-performance manufacturing, shaping metal is less about force alone and more about control under extreme conditions. At Kennametal, the 10-inch aluminum press machine represents the critical point where heat, pressure, and precision converge to define the final product. Operating with a capacity of up to 4,000 tons, this extrusion press forces preheated aluminum billets through high-precision dies, forming complex profiles with tight dimensional tolerances. The billet, engineered for uniform grain structure and alloy consistency, is heated to an optimal temperature range to ensure smooth material flow and minimize internal defects during extrusion. Process stability is maintained through advanced control of ram speed, pressure, and thermal conditions, allowing consistent wall thickness and surface quality across long induction runs. The die system, manufactured with CNC precision, ensures repeatability and geometric accuracy for both standard and custom profiles. Following extrusion, profiles undergo cooling, stretching, and cutting, correcting residual stress and ensuring dimensional integrity. In railway manufacturing, GR7 wheelset machining represents a critical phase where forged wheel blanks are transformed into precision components ready for high-speed and heavy-load operation. The process begins with rough turning, where excess material is removed to establish the primary profile of the wheel and axle interface. Advanced CNC lathes then perform finish machining, achieving tight tolerances on tread diameter, flange geometry, and bore alignment. Surface integrity is essential. with controlled cutting parameters, ensuring minimal residual stress and optimal fatigue resistance. Key dimensions such as wheel gauge, concentricity, and roundness are verified through inline measurement systems. Additional operations may include drilling, keyway machining, and final balancing. The result is a fully machined wheel set. In high-performance motorcycle engineering, forged wheel production on a Haas 5-axis milling platform focuses on aggressive material removal and precision geometry control. Starting from a solid forging, up to 75% of material is milled away, reducing mass while preserving structural strength across wide spoke designs. The use of a 5-axis machine, 3+1 configuration with B-axis movement, enables deep access into complex internal features and tight corners that conventional 3-axis systems cannot reach. This allows full machining in a single setup, including critical features such as the valve stem hole, eliminating secondary operations and alignment errors. High-speed machining with advanced look-ahead control ensures smooth toolpaths despite dense CNC programs, with some single operations running up to 2.5 hours. Consistent accuracy and repeatability are essential, as scrap rates must remain near zero. Edge finishing and surface detailing are completed directly in cycle, producing a functional, lightweight wheel with precise tolerances and no post-processing. Before an alloy wheel ever meets the road, its final identity is defined in the painting stage, where surface engineering meets aesthetics and durability. At GMP Italia, this phase transforms precision-machined rims into high-performance components capable of resisting corrosion, abrasion, and environmental stress. The process begins with surface preparation, including cleaning and chemical pre-treatment to remove contaminants and improve coating adhesion. Wheels are then subjected to controlled drying before entering the automated painting line. Using electrostatic spray systems, layers of primer and base coat are applied with uniform thickness, ensuring complete coverage across complex geometries. Finishes such as black, silver, satin, or diamond-cut effects are achieved through carefully calibrated application parameters. Following coating, curing occurs, where the paint polymerizes into a durable, protective layer. This curing stage enhances resistance to UV exposure, road chemicals, and mechanical wear. The result is more than visual refinement. It is a functional coating system that preserves structural integrity while elevating design, ensuring each wheel performs reliably under demanding real-world conditions. The Gabion mesh machine operates through a synchronized mechanical drive system designed for continuous double-twist weaving. A crankshaft and connecting rod mechanism drives gear trains and oscillating arms, reversing motion to create the characteristic twisted hexagonal mesh. Wire is fed forward via pin shafts spaced 6 centimeters horizontally and 8 centimeters vertically, forming uniform openings. A 22 kVA motor powers the system through a conical transmission, ensuring stable torque. At Bunorm and in Arwangen, large-scale machining is defined by the ability to control precision across extreme dimensions and mass. The facility integrates welded fabrication and high-capacity CNC machining,
enabling the production of complex steel structures and components with exceptional accuracy. In the fabrication stage, welded constructions are assembled with weights reaching up to 20 tons, ensuring structural integrity before machining. These assemblies are then transferred to advanced machining systems, including the DMU 600P Portal Machining Center, a 41-meter-long platform capable of processing workpieces up to 18 meters in length and 75 tons in weight. Equipped with multi-axis capability, interchangeable heads, and rotary positioning systems, the machine performs drilling, milling, and multi-face machining in a single setup, minimizing repositioning errors and improving geometric accuracy. The result is a fully controlled workflow where size, weight, and complexity are managed without compromising tolerance or productivity.
In precision heavy machining, CNC boring mills enable complex, multi-face operations within a single setup. This component, featuring an oval surface, multiple faces, and 5 critical holes, is machined through table indexing at 90-degree rotations, eliminating repositioning errors. Tight tolerances of plus to 0.05 millimeters are achieved using calibrated fine boring tools, ensuring consistent hole accuracy without repeated adjustments. The machine guarantees perpendicularity across all surfaces. The Umaro SCM 63/100 single-column vertical turning lathe is a CNC-controlled machine designed for large-diameter components. Reconditioned in 2003, it features a table extension up to 8,000 millimeters, enabling the machining of oversized workpieces. Built in Romania and located in Germany, offering reliable performance for heavy-duty industrial applications. Metal spinning is a precision forming technique used to produce hollow, asymmetrical components from flat metal discs. The blank is clamped onto a rotating mandrel and spun at high speed, while a hardened roller tool progressively applies pressure to shape the material along the mold profile. This cold forming process maintains material continuity, improving strength and reducing waste compared to machining. It is ideal for thin-walled parts, delivering high-dimensional accuracy, smooth surface finish, and efficient production of components such as cones, cylinders, and complex curved geometries. In precision sheet metal forming, metal spinning offers a highly efficient method for producing axisymmetric components such as large cowls. The process begins with the first stage spinning, where a blank is mounted on a rotating mandrel and shaped using lever spinning techniques. This approach provides greater mechanical advantage, allowing controlled force application for rapid material displacement while maintaining uniform wall thickness. As the part approaches its final geometry, the operation transitions to a conventional spinning tool, enabling finer control over surface finish and dimensional accuracy. This stage refines contours, eliminates minor deviations, and ensures tight tolerances. The combination of lever-assisted forming and precision finishing results in reduced forming time, improved structural integrity, and minimal material waste, making it ideal for large-diameter, thin-walled components. In large-scale precision grinding, the Haas multi-grind system redefines capability by combining extended workpiece capacity with high-accuracy machining. Designed to process components up to 3,200 millimeters in length, the machine integrates up to 3 steady rests to suppress vibration, enabling stable grinding of long, slender shafts and spindles. A single clamping setup ensures full process consistency from roughing to finishing, including right flange machining. The automatic tool changer supports multiple grinding strategies, allowing complex geometries and mixed sections to be produced without interruption. Adjustable coolant nozzles optimize thermal control, improving surface quality and tool life. Compared to traditional milling or turning, the system reduces tooling costs and efficiently processes hard-facing materials, shortening cycle times while maintaining tight tolerances.
At ARR Machining, valve production spans from compact 2-inch components to massive 25-ton assemblies, requiring extreme precision across varying scales. Advanced CNC machining centers handle turning, milling, and boring operations, ensuring tight tolerances on critical sealing surfaces. Multi-axis control enables complex geometries, while rigorous inspection guarantees dimensional accuracy.
At Keenan Metal Foundry, aluminum billet production is driven by controlled melting and precision casting technologies. Raw aluminum is processed in high-capacity furnaces, where temperature and composition are carefully regulated to achieve optimal purity. The molten metal is then transferred into casting systems, forming extrusion billets with uniform structure and minimal defects. Advanced filtration and degassing processes remove impurities and gases, improving mechanical properties. Continuous monitoring ensures consistent billet dimensions and metallurgical quality, meeting international standards. The result is high-purity aluminum billets engineered for demanding extrusion applications across construction, automotive, and industrial sectors. In modern heavy industry, the production of large-diameter steel pipes, 16-inch diameter, 12.7 millimeters wall thickness, is executed through a rigorously controlled sequence of forming, welding, and inspection operations to ensure mechanical strength, dimensional accuracy, and long-term reliability. The process starts in the plate storage yard, where steel plates are handled using vacuum crane systems, allowing safe, non-invasive lifting while preventing surface deformation or contamination. The plates are then introduced into a 3-roll bending machine, where progressive rolling gradually transforms flat steel into a cylindrical form. This forming stage is carefully controlled to avoid residual stress concentrations. A post-bending calibration process follows, refining roundness, correcting alignment, and ensuring that longitudinal edges are properly matched for high-quality welding. The pipe then advances to the welding stage, beginning with internal welding, which establishes the root seam and ensures full penetration. This is followed by external welding, where automated welding machines complete the joint with consistent bead geometry and structural integrity across the entire seam length. After welding, a visual inspection is conducted to identify any surface discontinuities. The pipe is subsequently processed through an expander machine, which applies controlled radial force to improve circularity, enhance dimensional precision, and relieve internal stresses induced during forming and welding. Next, the pipe undergoes post-washing, removing scale, slag, and contaminants from the surface. A critical hydrostatic pressure test is then performed to verify leak tightness and confirm the pipe's ability to withstand operational pressures. To ensure internal quality, advanced non-destructive testing methods such as ultrasonic testing and real-time X-ray inspection are applied to detect subsurface defects. Finally, end beveling machines prepare the pipe edges for field welding, followed by a comprehensive final inspection that validates geometry, surface condition, and compliance with international standards, ensuring a high-performance pipeline product.
In HVAC duct manufacturing, Sente Machine's oval duct production system integrates automated forming, precise geometry control, and flexible shaping technologies. The process typically begins with flat galvanized sheet metal fed into a multi-roll cylinder machine, where progressive bending between rollers forms the initial oval profile with high dimensional consistency. A PLC-controlled interface governs the operation, allowing operators to input the major and minor diameters. The system automatically calculates sheet development dimensions, eliminating manual errors and ensuring repeatable accuracy across production batches. For applications requiring conversion from circular ducts, an ovalizing unit applies controlled deformation using calibrated rollers or hydraulic force. This reshaping process maintains airflow efficiency while reducing installation space, combining the aerodynamic advantages of round ducts with the compactness of rectangular systems. Typical material specifications include sheet thicknesses up to 1.0 millimeters and widths up to 1,250 millimeters, with a minimum bending radius of R45 millimeters, ensuring structural integrity without cracking. The result is a precisely formed oval duct with consistent cross-section, optimized for airflow performance, structural stability, and efficient installation in constrained building environments.
At JB Stahl Service, the integration of the Stiegl ProMaster 3D cutting system defines a highly efficient multi-process steel fabrication workflow. Operating within a 3,000 by 12,000 millimeters work area, the machine is equipped with dual Sabora Professor 255 HVAC power sources, enabling simultaneous plasma and oxy-fuel cutting for diverse material thicknesses. The system features 4 independent tool supports. The primary unit utilizes a multi-3D head capable of advanced 3D plasma and gas cutting, allowing beveling, contouring, and complex edge preparation in a single pass. Secondary supports handle 2D plasma and oxy-fuel cutting, optimizing productivity for both precision profiles and heavy plate processing. A pipe rotator system extends capability to cylindrical components, enabling accurate rotational cutting operations. Control is managed via the Smart Control wireless interface, ensuring flexible machine operation and real-time adjustments. Complemented by the VX standard system for additional 2D cutting tasks, this setup delivers high throughput, repeatability, and versatility, supporting JB Stahl service in producing complex steel structures with consistent accuracy and reduced production time.
The Valen ABV 52-inch top entry ball valve is engineered for high-integrity pipeline applications, combining robust construction with advanced sealing technology. Manufactured as a one-piece cast body, the valve features a double block and bleed configuration, ensuring isolation and pressure relief under critical operating conditions. Key design elements include an anti-static device, anti-blowout stem, and dual sealing system with O-rings and a secondary pure graphite seal. Emergency sealant injection ports on both seats and stem enhance reliability during operation. The seats utilize a double piston effect with Viton AED seals and Devlon inserts, while the ball is constructed from carbon steel with a stainless steel overlay for corrosion resistance. Manufacturing quality is validated through extensive NDE inspections, including supported by 3D scanning systems for dimensional accuracy. Welding procedures comply with ASME Section 9 and EN 15614 standards. Performance testing under API 6D includes hydrostatic shell testing at 154 bars and seat testing at 113 bars, achieving zero leakage. The result is a high-reliability valve optimized for durability, sealing performance, and inline maintenance. In CNC-based toy manufacturing, precision machining transforms raw material into detailed, repeatable components. The process begins with CAD modeling, followed by CAM programming to generate toolpaths optimized for small-scale geometry. A CNC router or milling machine then cuts the toy from wood, plastic, or soft metal using high-speed spindles and fine-cutting tools. Multi-axis control enables smooth contours and intricate features. After machining, parts undergo sanding and finishing to improve surface quality and safety. The result is a dimensionally accurate toy with consistent quality across high-volume production runs. At Mechanica Gervasoni, advanced valve component manufacturing is structured around a fully integrated engineering and production system.
Operations begin within the technical office and CNC department, where machining programs are developed and optimized, supported by continuous input from research and development to refine materials and processes. Core production focuses on ball and seat components, which undergo precision machining both before and after weld overlay operations. Surface enhancement is achieved by automated TIG, MIG, and saw welding, with 16 certified stations compliant with UNI-EN ISO 3834-2. High-performance alloys such as Inconel 625, duplex, and super duplex are applied using FANUC robotic systems, ensuring uniform deposition and metallurgical integrity. Post-overlay machining restores tight tolerances followed by advanced coatings including tungsten carbide and chromium carbide applied via HVOF technology to improve wear and corrosion resistance. Subsequent grinding and precision lapping of seats ensure optimal sealing performance. Quality assurance is comprehensive, including die penetrant inspection, thickness verification, and detailed traceability via heat number, drawing number, job number, and serial number tracking. This integrated workflow guarantees high reliability, durability, and compliance with demanding industrial standards.
The Tesker Model 742 die thread roller delivers high-force precision forming for large components. With up to 340,000 pounds rolling force and a 75 horsepower variable speed drive, it efficiently forms threads through cold deformation. Setup includes die alignment and digital size calibration with cycle monitoring. In testing, the machine rolls a 4.5-inch diameter, 1.5 TPI single-start Acme thread in 1045 CDS steel, demonstrating deep, accurate thread formation. The system supports in-feed rolling up to 12-inch diameter, while a 20-foot bar handler and integrated crane enhance productivity. Push-button controls ensure precise, repeatable sizing. In deep foundation construction, precision and productivity converge in the fully automatic bore pile cage welding machine. Engineered for heavy-duty reinforcement cages, this system processes longitudinal and spiral wires directly from coil, eliminating manual pre-cutting and ensuring uninterrupted production flow. At the core is a 1000 kVA medium-frequency electro-spot welding unit operating at 1000 Hz, delivering stable energy input, deep weld penetration, and consistent joint integrity even with wire diameters up to 20 millimeters. This high-frequency control minimizes thermal distortion while maintaining structural strength across large diameter cages used in bored piles. Automated synchronization between feeding, rotation, and welding modules enables precise pitch control and uniform cage geometry. The off-coil configuration significantly reduces material handling time while increasing throughput, making it ideal for infrastructure projects requiring high volumes of reinforcement. The result is a robust, dimensionally accurate cage with superior weld quality, optimized for demanding geotechnical conditions and high-load foundation systems.
The Stiegel pipe rotator is a precision positioning device designed to support and rotate pipes during thermal cutting operations with oxygen, plasma, or advanced multi-3D heads. It accommodates pipe diameters from 50 to 900 millimeters, wall thicknesses from 1 to 100 millimeters, and lengths ranging 0.5 to 12 meters, ensuring high flexibility across industrial applications. The system stabilizes cylindrical workpieces and enables controlled rotation, allowing accurate circumferential cutting, beveling, and complex profiling. Adjustable supports and synchronized rotation improve cutting quality while reducing operator intervention. Pipe rotators are widely used to enhance precision and productivity by maintaining consistent positioning during machining or welding processes.
In a modern pressing environment, the warm-tone record press by Viral Technologies transforms vinyl production into a highly controlled, data-driven process. Setup begins with precise installation of stampers and calibration of parameters such as temperature, pressure, and cycle timing, ensuring alignment with the specific audio master. A preheated PVC compound is extruded into a puck and positioned between stampers. Under hydraulic force, the material flows uniformly, replicating microscopic groove details with high fidelity. The system then transitions into a controlled cooling phase, stabilizing the record and minimizing defects such as warping or surface noise. With cycle times as low as 24 to 25 seconds and automated stacking and trimming, the warm tone enables continuous, high-efficiency production. Integrated features such as quick change stampers and the Adapt monitoring platform allow rapid setup changes and real-time performance tracking, optimizing uptime and consistency across production runs.
In post-tensioning systems, the Centimachina ARD duct machine is engineered to produce corrugated flexible ducts that house pre-stressing tendons within concrete structures. The process begins with galvanized steel strip, 0.35 to 0.50 millimeters thickness, fed continuously into forming rollers, where spiral corrugations are created to enhance crush resistance and structural stability. A synchronized drive system shapes and locks the seam, forming ducts with diameters from 50 millimeters up to 135 millimeters, while maintaining consistent geometry at feed speeds between 4 to 39 meters per minute. The resulting ducts provide a protected pathway for tendons, ensuring durability, corrosion resistance, and reliable performance in post-tension concrete systems.
The next double-wall corrugated line is an advanced extrusion system for producing high-performance plastic pipes. Thermoplastic materials such as HDPE or PP are melted in extruders and processed through co-extrusion, forming a smooth inner layer and a corrugated outer layer for strength. The material passes into a corrugator mold system, where vacuum forming creates the ribbed structure. A controlled cooling stage stabilizes dimensions, followed by automated cutting and stacking. With PLC-based control, the line ensures precise temperature, pressure, and speed regulation, delivering lightweight, durable pipes for drainage and infrastructure applications. The CRAW pipe production process is based on advanced helical extrusion, spiral wound technology, specifically developed for manufacturing large-diameter thermoplastic pipes with high structural performance. Production begins with high-density polyethylene, or HDPE, or polypropylene, PP, granules, which are melted in an extrusion system under controlled temperature conditions. The molten material is then continuously applied onto a rotating mandrel, forming the pipe layer by layer in a spiral pattern. Unlike conventional pipe manufacturing, CRAW technology allows the creation of custom wall structures, including solid walls or profiled, structured walls with internal cavities. This enables engineers to optimize ring stiffness, weight, and material consumption according to specific project requirements. During winding, the extruded material is fused seamlessly, creating a homogeneous, joint-free pipe body with a smooth inner surface suitable for fluid transport. Integrated socket and spigot ends can be formed directly during production, enabling efficient electrofusion joining in the field. After forming, the pipe is cooled and dimensionally stabilized on the mandrel. Additional layers may be added through co-extrusion, improving UV resistance or inspection visibility. The final stages include cutting to length, surface inspection, and quality verification to ensure compliance with international standards. CRAW pipes can be produced in diameters from DN 300 mm up to DN 5000 mm, offering exceptional flexibility for infrastructure applications. This process results in lightweight, corrosion-resistant, and highly durable pipes, widely used in sewer systems, drainage, marine outfalls, and industrial fluid transport. From raw log to refined wood product, GSS WoodX technologies deliver a fully integrated processing chain for solid timber manufacturing. The workflow begins with SGM industry debarking lines, where logs are cleaned and prepared, followed by Dynacoat petting systems that segment timber with high efficiency and minimal waste. Precision is maintained through NEVA CNC sharpening machines, ensuring bandsaw blades retain optimal cutting performance. NEVA resaws and mini sawmills then process logs into lamellae, ready for further refinement. Four-side planers and profiling machines create uniform dimensions, while CNC lathes and multi-axis Intorex systems shape complex solid wood components with high accuracy. Structural integrity is enhanced through finger jointing lines by YNF, enabling the production of longer, defect-free elements. Pressing systems, both cold and hot, bond materials under controlled conditions, ensuring durability and stability. Finally, calibrating and sanding machines deliver smooth, consistent finishes. The result is a streamlined, high-precision production ecosystem optimized for efficiency, flexibility, and premium quality wood products. At the DeChambeau smelter, aluminum is produced using the Hall-Héroult electrolysis process. Alumina is dissolved in molten cryolite at around 950 degrees Celsius, where high direct current separates aluminum from oxygen. Automated systems control current, temperature, and alumina feed to ensure stable operation. Molten aluminum is extracted and cast into ingots, while closed-loop cooling and gas treatment systems enhance efficiency. In modern bauxite mining, efficiency is no longer driven by blasting, but by precision cutting. The Surface Miner 2500 SM operates in a fully continuous, blast-free system, selectively extracting material with compressive strength between 20 to 70 megapascals, while maintaining consistent quality and minimal dilution. With a cutting width of 2,500 millimeters and depths up to 500 millimeters, the machine produces up to 9 million tons annually using the side casting method. Material is cut, crushed, and strategically deposited to form in-pit stockpiles through sequential passes, reaching widths of 31 meters and densities around 35 ton per meter. This approach protects ore from rain, enhances natural drainage, and improves loading efficiency. Alternatively, the 2200 SM enables direct loading. In precision steel processing, surface quality begins long before finishing, and that is where the BTM 350 round bar peeling machine plays a critical role. Operating with multi-blade cutting heads, the machine performs continuous peeling with controlled depth, typically ranging from 0.5 to 5 millimeters, depending on material condition. Feeding speeds can reach up to 5 meters per minute, while maintaining tight diameter tolerances around H9 to H11 and surface roughness as low as RA 1.6 to 3.2 micrometers. A robust spindle system combined with hydraulic clamping and automated feeding ensures stable bar alignment and minimal vibration during operation. The process significantly improves roundness, straightness, and dimensional accuracy, critical for downstream machining or forging. In high-precision furniture manufacturing, Bentwood forming integrates thermal treatment and controlled deformation to produce complex, load-bearing wooden components. The process begins with steam conditioning at approximately 100 degrees Celsius, where heat and moisture plasticize lignin, allowing the wood fibers to flex without fracture while preserving grain continuity and structural strength. For deep curves and asymmetric geometries, rim bending, Taiwa bending is applied. The workpiece is secured with a steel backing strap and rotated along a forming jig. This method redistributes tensile stress, preventing surface cracking and enabling tight radius bends with high dimensional accuracy. The result is a smooth, continuous grain structure that enhances both strength and visual quality. For more complex three-dimensional forms, manual bending techniques are employed. Operators carefully control force direction, magnitude, and fixation points to achieve stable geometry. This method is particularly effective for custom or irregular shapes where automated systems are limited. In the case of thin sections and gradual curves, hot press bending is utilized. Steam-softened material is placed into heated molds and compressed using hydraulic presses, simultaneously shaping and drying the component. High-frequency drying systems accelerate moisture removal, reducing cycle time and minimizing deformation.
Finally, press bending stabilizes the structure by relieving internal stresses. The formed component is fixed within a mold under hydraulic pressure until the geometry is permanently set. This multi-stage approach ensures high strength, repeatability, and refined surface quality in advanced bentwood production.